Welcome to deep learning. Today we're going to continue to talk about the transformer and in particularly how to be learning sequences. So we saw this before in a previous lecture that learning sequences of data like words in a sentence or stock price can usually be done by predicting the next word or next price or next token in the sentence. So for example, here we have an input sequence x1, xn. We'll have an encoder and we can try to predict which one is the next sequence token. Also, if we want to translate a sequence into another, like for example, we could translate one language into another, then we provide the sequence to an encoder. This encoder will feed to a decoder, and the decoder will produce the second sequence, the output sequence that we want, one item at a time, and it will also receive the previous sample that it has produced so that it will try to figure out what the next one is going to be. We also saw what is the tension in terms of, for example, looking at a sentence in the previous lecture. Let's say, for example, that we had a sentence like this. Like the animal didn't cross the street because it was too tired. So one important component in neural network that we need to understand to really comprehend all the details about the transformer is like how can we actually try to make sense of a sequence that has items that refer to other items in the sequence. So for example, when we look at this sequence and we saw the word yet, we don't know if it's referring to the animal or, for example, the street. And we need to figure that out. We need a neural network that is able to do this. And so if we were to use a simply linear layer, for example, that take all of this input at one point and look at the sequence, we're not going to be able to really comprehend the details between, where the word hit was referring to, because we didn't have a chance to cross-correlate the value of this word with the value of the other one. So we need something that can do that. And so this is really the point, is like what we want to do is we want a module that can find a relationship in the sentence. When we see the word it, we want to figure out what are the most probable previous words that we used that refer to it, right? And this is a tension because it basically tries to point to a specific item in the scene, a specific item in the sequence that another item is referring to. And so we want to do this for all the words in a sequence, but also for many sequences that happen one after the other. And so we're going to have to do this large scale. And this is really what makes the transformer neural network so special, is this attention module in particular that allows it to do this. So one of the modules that you see in the transformer neural network is the multi-headed attention. And this module is really the center of the transformer, GPT, large language model. And so I think we really need to understand it. And don't be scared by this diagram on the right. It's a little bit dry, but we'll go through it and step by step and really try to understand. Multi-headed attention is really the most important component in the sequence. So in particular, let's look at this sequence. The animal didn't cross the street because it was too tired, right? And so I'm going to try to make sort of a matrix of importance between one word and the other, right? And the first thing we're going to do is we're going to turn every single word or every single part of a word into some embedding. So these are embeddings are in green. And this is done because the neural network only understands numbers, so we're going to need to give it a vector. Here I'm representing this embedding as just one giant number, but in reality it's going to be a vector of a few numbers, right? And so what we're going to do here is that I'm going to look at the words and how they refer to each other. So you'll notice that they're all one in the diagonal, because basically D and D are correlated, are the same word, so the correlation is 1 basically. But when I get to animal, then I can correlate the word animal to the previous word D, for example. Or when I get to didn't, I can correlate the word didn't to the previous 2 other words. Notice I'm not looking at the words ahead of me, because they didn't really, they haven't been outputted yet, so it would be a little bit unfair if I look at that. But it depends on what kind of neural network we're going to do. So if it's an autoregressive model, this makes sense. But if it's a translation model, for example, we might have an entire sequence available before time. In any case, here what we're trying to do is I'm trying to basically create a representation or some kind of attention weights between the words in this sentence and the same words in this sentence. And how can we do this? And I think it's very important, and this is really the key of understanding neural attention. So actually, by doing what I showed you just now, we already calculated a part of this multi-headed attention. This is what it does. In this query, key and value, Q, K, and V are just the projection of the same input sequence, actually. And so in the query and key, what happens is that we're going to set the query here and the key as horizontal and the other one as vertical, and then we're going to compute a matrix of correlation between these words and their embedding, actually, right? This is just a toy example, by the way. It's not exactly what happens, but it's pretty close. So by doing that, that matrix, it's sort of like a byword matrix, right, of correlations. Then we actually implemented this part of the multi-headed attention. The second part is actually multiplying these weights by another representation or another projection of the input called the values. And then basically this applies weight to the input sequence and tells you which part of the sequence was important to this specific relationship. For example, when we're looking at the word it, it will maximize street and animal as opposed to other words. Another ways of looking at multi-headed attention, which by the way it's called multi-headed because it actually has multiple of these heads in parallel, is we can look at the single head represented here. And so what we have is we have an input, which could be words. Those are embedded. Actually, this is a word embedding already, so this is already the sequence. And we can project it with a matrix and basically turn it into some embedding. So the same input is embedded into something called the queries, to something called the key, and something called the value. So as you can see here, query and key then, they just form a sequence of items that are multiplied then together. And then these are normalized and passed by softmax, but effectively, basically, what they create is a matrix of weights. And this matrix of weights is then multiplied by the value, another projection of the input, to create an output. The transformer itself, at the end of the day, this is what we see in the transformer paper, all you need is attention paper from Google in 2017. And it looks a little bit scary at the beginning, but let's analyze a little bit in detail every single section. First of all, this model that you see here is actually a sequence-to-sequence neural network. Okay, so it's composed, it takes an input sequence and it's going to output another sequence. And so let's first look at this red portion here. This is actually the encoder, which could be used by itself, and it takes the input sequence and in parallel it basically embeds all the input sequence into some final amount of vector here that are sort of summarizing all the input sequence. Okay, and this could be used by itself to encode, for example, text in a vector, right? The second part of this of the transformer on the right side is the decoder. So the decoder is actually going to output the second sequence, the output sequence that we want, and it's autoregressive, means it fits on itself. So once it produced the first element in the sequence, it's also going to take that first element to produce the second element of the sequence. And this is really how LLM are implemented, like large language model or language model in general. They're implemented by using a decoder-only neural network. And look at this element that here in red of the transformer. This is actually an element that we see repeated in transformer many times. In fact, I think in the original transformer paper repeated 6 times on the encoder and 6 times on the decoder. This is actually composed of 2 parts. It's composed of the multi-headed attention, but then it's also followed by a very simple neural network. It's just actually a 2-layer MLP neural network, the kind that we've seen many times at the beginning of this lecture. And notice also that these input have a pass-through, like a residual network. So the input that comes here to this multi-headed attention is also passed through to the output, and even the feed-forward basically input is passed through. And so this is like, it's a way like in residual networks, so that information can pass to multiple layers untouched and can be processed by multiple parallel paths of this transformer. So in fact, we're going to have six of such layer, or 12 of such layer, or 24 of such layer in very large language model. And also, I want you to also focus at this part of the neural network, so the output of the encoder, how it fits into the decoder. As you can see, is after an initial multi-headed attention in the decoder, the output of the encoder is used as query and key in the rest of the decoder. And why? Well, that's simply because here we're doing a translation, so we're going from a sequence like a language, English, to another language like Spanish, and we want to embed the input sequence and use it to condition the output of the second sequence that is translated. So this makes perfect sense. This is how you will see implemented, and it's actually creating the weight matrix for this attention, but actually the value come from the second language, let's say. And then as the last thing that I want to mention about the transformer is the input embedding. So input embedding, like words, are embedded in each one into some vector, for example, 200 the numbers, right? And then because this transformer doesn't really have a clock inside, or it's processing a lot of this information without having sort of like a timer or index into the sequence. It doesn't really know the position. So what we do instead is we add some sine waves, some positional embedding, sine or cosine combination to the input. That's sort of like giving an idea of where it is in the sequence, and this helps the transformer to learn. This is actually what constitutes the initial encoding, and this is what actually goes into the transformer layer. So I just wanted to point out it's not exactly word, it's just this specific embedding that is done in the neural network. So I hope this helps you to understand the transformer and all these parts, you'll see that it's a really great invention and probably one of the best neural network invention in the last few years.